I'm going to give just a brief introduction so you can have a little idea of my perspective on soil health. I grew up in a little town between along the Rio Channel between Abiquiu and Espanol, and we farmed 7 acres of vegetable crops, and so I had the privilege as a little kid of being a fifth-generation farmer farming in that area. So my perspective on soil health is something that I was taught from my dad, my mom, and my grandfather, but it's something that has quite a lot of generations. So a lot of the stuff that I'm going to talk about, Brendan talked about, Jay and others will cover, are practices that I had first-hand experience in terms of diverse cover crops, crop rotations, irrigation, and water plant management, composting, grazing, and whatever. So by the time I started with the agency almost 24 years ago, my mind had a different view of soil management. It was based on a proven way of farming. Based on the fact that we farmed that 7 acres for 30-some years, and that's the way we farmed those acreage and produced enormous amount of all types of vegetables that we would sell from June all the way to the last part of October at Solomon's, Santa Fe, Taos, and Farmers Market. Plus, we would sell to all kinds of clientele. And this came from 7 acres, so we grew an enormous amount of food, almost essentially with no chemicals, following a system of conservation management practices that are very, very sustainable. So my goal today is to share with you what we are doing in New Mexico, and we've got a long ways to go. We've got a lot of people to educate and a lot to learn from each other. And before I go into this topic of soils, another thing I want to emphasize is that from 1990 to 2001, I spent 12 years straight as a field agronomist in the Seal Valley, in the Las Cruces area, working with farmers all along the Seal Valley, El Paso, and towns. And the entire 12 years was under a special project, which means that I had the opportunity to work with strictly on salinity, water conservation, irrigation systems, and a bunch of other property systems to demonstrate soil health and water quality issues. This 12 years that I spent there working with a lot of very prominent farmers, and I'm getting some of the most useful learning experience because I've been able to use that background in the last 10 years in working with our field office, the Mexico State Specialist Extension and others, to jointly bring the level of soil health and white soil report to manage soils in a very intentional, methodical way, and being able to connect all the pieces together. So before I go starting here, I want to emphasize that for myself, when we were training on it, it's boiled down to it for a lot of trial and error practices, and getting a lot of input from a lot of farmers and what have you. That over 5 years, we've had the opportunity of presenting soil health workshops 64 times, throughout New Mexico. That doesn't mean we finish doing your soil health, we're ready to tip on the iceberg, because now we have a lot of questions and demonstrations that we're currently doing right now. And there's now more questions and more interest as never before, but we have a tremendous learning curve to pursue in understanding what is soil health. I want to start off here again by going through a process base that we use in New Mexico to try to connect us together. And the emphasis that I want to start off with is that one thing that we know for certain, in New Mexico, we have had, the last 2 years, the worst droughts in the state's history. And we're in big trouble. And we have on the east side of the state, in the Clovis, Portales area, where we have large zero pivots and large areas, we have a problem where we're running out of water, where we have a lot of aquifers depleting dramatically. So we have an issue with water. Major focus of what I want to talk about is why soil health is so important to understand water conservation and water quality. I'll give you an example. Some of our engineers and that work in the Clovis area tell me that 7 to 10 years ago, some of our wells were pumping up to 1,250 gallons per minute. Today, some of those wells pump 50 gallons per minute. And some are connected up to 10 to 12 wells together to run one center pivot. So what that tells us there is that water is an issue, right? I mean, how many wells do we want to connect from one center pivot to go across from the area issue when we have a problem with water?
You got a question whether or not this one will be better.
You can set it up there. So I'm bringing up the issue that we're facing in New Mexico. Right now, our Elephant Butte Dam, which is our largest reservoir in New Mexico, can typically hold 2.2 million acre feet. The last time it was in the mid-90s. still. It's better. Okay. Can everybody hear me? Is that better? Water issues in Mexico. Last year, they gave our irrigators in the Mesial Valley, which is the most exclusive area of natural way in the Mexico part. They gave them 2 irrigations, 4-inch application each one, so you already know that you don't have a well water, you're in trouble right now. Because prior to that, for all the years that I worked there, the average farmer would get 4 to 5 acre feet to grow their crops. So now we're pumping aquifer water that's very salty, sometimes 3 times as salty. As soon as you go to pumping water, you no longer have the flow and the volume of surface irrigation. Now it changes the dynamics of the water quality. Right, because you have a higher salt content, higher leaching fraction, but a system that can't irrigate as efficient. So I'm just trying to paint a picture for you of where we're at. Right before I came up here, I talked to our folks at the irrigation to do the survey on soil survey for our state, and they mentioned that the outlook for New Mexico is at this time not good. So that for all of from the health and youth to south, at this point they're not making any allocations of water. The water that we do have will be passing right through most cruises, and it'll be allocating the water that we owe or have on compact to pass through Mexico, right? So I mean, we could potentially be pumping all the water this year from the aquifer, not from the health and beauty, so this changes a little bit. If you come up further up the Rio Grande, the Middle Rio Grande Conservancy District in the area of Los Lunas and those areas, this year some of our producers have the water cut off like 10 weeks, right? So you can see that if you're someone growing alfalfa or what have you, 10 weeks lack of water is a big change. So keep the issue of water for us is a major issue, water quality, irrigation system efficiency, and the importance that the producer has to have a good understanding of what this is going to mean with this kind of issue. So soil health and water conservation and water quality, try to keep that in mind. So I'm giving you my perspective on how I grew up, on the special projects that I've had, and I had an opportunity working with hundreds of producers in New Mexico, that one of the biggest needs that we've seen after 6 years of doing soil health is an understanding of soil health is not really well understood by a lot of people in terms of the detail that we should know about it. And if you look at it over here, now I don't know whether you can see this picture, but here's the slate test this morning that we did. Our objective is that we want a soil that's high in organic matter by good management practices that add a lot of carbon to the soil, based on all the decisions on it that we put in the soil. So the end result is that we have a healthy soil that does not fall apart. Okay, that's our main goal. The other thing here, if you can see here, there's a grain. This is a macro aggregate. If we actually measure the distance, this might be anywhere from 3 to 5 millimeters in diameter. And you can literally see the coarse grains of sand, and then you can see smaller grains in there, and then you can see these other little grains, almost the same size as sand. And if I blow that up, you'll be seeing a microaggregate. It's actually a picture taken by Dr. Christine Nichols, and it shows all the white spots of the lake that is showing as white. So the microaggregate is made up of all of your clay particles, silt, a few very fine sand grains, and your humus and other organisms that are compacted together. That microaggregate is within a component of a macroaggregate. Okay, so you see then that before we go into how much water a soil can hold, water holding capacity, what kind of salinity is in there, what kind of pH, cation exchange capacity, anything that we want to think of. We want to find out what is the living conditions in there for a lot of the soil biology that you can't see with your eye, the invisible world of soil biology. Right? One of the hard things about selling the concept of soil health is so hard to understand that a healthy soil with a few grams of soil can have millions and millions and millions of bacteria, right? All kinds of species of beneficial nematodes, ciliates, protozoa. You have all kinds of critters in there. So one of the things that we're interested in, when we're interested in systematically designing a conservation system, want to call it a soil health management system, is we want to get very site-specific local facts that pertain to a given community and say this is the way our picture looks. And in that environment, we decide how we are about to manage a certain soil type to its soil health potential. And we come with it we take off our rose-colored glasses because in some cases we have very serious limiting issues, like water. The water is too salty. In New Mexico, we have long growing season. For example, in the Mesilla Valley, they will be planting June by the middle of March. The pecan trees will be blooming by the latter part of March. And they'll be harvested in the end of November. So yeah, we have a lot of heat limits of very hot days, and we have an enormous potential to cause organic matter decomposition or oxidation. But we have very little water to grow organic matter. So unless we do a lot of practices right, we have a lot of things against us. We have little water, we have long growing season, very dry hot climate, hot temperatures, and many times we don't have the markets for the kind of crops we want. And so all of these variables that we're looking at, how do we site specifically begin to decide what is happening locally in a certain place? So you can see that we're interested in this macro aggregate. That's what we want as an ultimate goal to assess your field. Macro aggregates are an indicator that your soil is at a high level. A lot of micro aggregates means that there's a lot of tillage going on and your soil will collapse. And you illustrate this, you'll get soils that develop thick crust and are very unfavorable to the farm. And the other thing is that soil health can be done on every soil type. We've been able to improve soil type on very sandy soils, and very clay soils, and all the other soils by comparison are much easier to improve. We're able to grow on, for example, alfalfa, pecans, and other crops on very awful clay soils or managed for soil health. Likewise, the same thing for sandy soils, coarse sugar sandy soils. When managed for soil health with good management practices, we're able to manage extreme soil types well. And that means we're able to do the other soil types much easier because they have a lot of inherent properties that make them more favorable to farm. So keep that in mind. Please keep this picture in mind here of the background here with a lot of domain, get up on your second slope. Get up on your primary, your clay, your silt, humus, and other items. And remember that microaggregates, when they're part of a large microaggregate, that's when they're protected inside the aggregate from being oxidized. And this whole aggregate right here, as you can see, when I get one macroaggregate compared to another, the spore spaces between them are called macropores. Now, if we have that kind of a soil as our end game, we will have the environment, the architecture, to where all kinds of living organisms can live between the aggregates, in the aggregates, right? And this environment will allow us then, for us to have good oxygen coming into the soil by diffusion, because there's a lot of porosity, and so we don't have nothing restraining oxygen from coming into the environment. Remember that the roots and a lot of the biology of the soil are heterotrophic organisms. They're having to respire, taking oxygen. So one of the reasons we want healthy soils, we don't want at all, nothing impeding oxygen coming right into the roots of the rhizosphere, or affecting none of the organisms that are in the soil from breathing, because the majority require oxygen to breathe. And if we have good soil structure, that means we will have good infiltration, good aeration. This will mean you have good till, the soil is very favorable. And the roots will easily work between macroaggregates and in between the aggregates. They will send their mycorrhizal hyphae, and they'll send their feeder roots and root hairs, and they'll grow very easily because there's very little resistance. So it's able to go into a macroaggregate and a microaggregate in between the aggregates and easily move through the soil, which means that the plant will take very little energy to put a root mass to extract the nutrients of the water. It'll breathe, it'll release carbon dioxide, and it'll have an environment that's conducive to soil health. So soil health means is that you have an environment where the temperatures are lower, and that's what you're going to have. You have good ground cover, good aggregate stability. You're going to have temperature, instead of the temperature being in New Mexico, where we measure temperature as high as 110, typically till field. That same soil type on the field that was managed well, temperatures at 75 to 80 degrees. So if you're a living root or a mycorrhizal fungi or an organism or bacteria or what have you, and in New Mexico and it's very low humidity, it's a hot, windy day, and you have a good residue of either surface residues or a living plant, and you have a well-aggregated soil that's breathing and releasing carbon dioxide, and you have cooler temperatures, you'll have an environment where the nutrient cycling of that environment is optimized. So when you simply put in a soil thermometer 1 inch into the soil, you will see that a healthy soil can be 20-some degrees lower than a soil that falls apart. Not only that, so if you have a lower soil temperature, the nutrient cycling and the ability to use water efficiently is dramatically improved. If your soil is tilled more than is necessary, and sometimes it's necessary because of the kind of cropping systems we haven't developed the science to go over there, you lose a lot of the evaporation. As was mentioned, the volatile evapotranspiration, right? We don't like the evaporation part, we want the transpiration to be on it. So we need cool temperatures, we need covered soil, we need an environment where the entire ecology of the root system and the microbes are at their optimum game. So this whole thing of, before we talk about all the various types of conservation practices using compost, and we're doing a lot of this kind of demonstrations in New Mexico in order to tailor specific environments to what the actual need is. But always on the premise, when we work with our producers or issues specialists or extension consultants and working with many partners, our fundamental goal is we want to set as a goal, we want soil health, and it means this, that from the surface down, as much as we can, on that top few inches, we want macro aggregates that are water stable, consisting of micro aggregates that are insulated, protected, that get very little disturbance from more than is needed. Because that's what we're about to evaluate. When we evaluate the temperature, if I insert a tensiometer in the soil at different depths and I'm measuring the nutrient potential tension, all I'm simply measuring is how tightly is water bond between the macro aggregates, the micro aggregates, in the micro aggregate, and the macro aggregate. We're trying to find out how available water is. The more water the soil has because of higher water holding capacity, the more water it has available, right? The lower the temperature is, the less water it takes to extract nutrients and send them up to the plants without having to use so much water to cool off. So we're going to relate every single variable, whether it's pH, whether it's salinity, whether it's nutrient cycling, whether we're talking about nitrogen losses. Always always at the top of our head is what would happen if we could shrink you down and put you in there to see the microbiology, you would see it with your own eyes, and you saw the porosity of the microbes in the water. You saw how tight the water was held, how salty it is, and what kind of fertilizer transformations are going on, and which organism is eating which, and all the nutrients are getting into the roots. If we would then focus all of our attention to how we are about to analyze soils, then you will say, okay, a good soil will have water stable aggregates. Let's make decisions then that give us the best, healthiest soil in light of that. Inside this aggregate, we're interested in a lot of analysis of what we're about to extract out of the soil. Okay, go ahead. Okay, so I'm going to give you an example here, and I'm going to use one of many. My goal here to strictly cover the science and the concepts of the principles. In New Mexico, we have all kinds of water irrigation systems. That's just New Mexico. It's long-standing history. We have all kinds of irrigation systems. We have all kinds of cropping rotations. We have all kinds of different locations, the north to the south. We have water quality shortages in some areas and some areas not. We have salinity changes. We have water quality that's different from one area to the next. And so we have all this complicated issues working on the system. So I thought that for the sake of in soil ecology or agroecology, the first rule that we come to is that everything is related to everything else, which means it makes it very complex. Okay, the question that we always get from our farmers and NRC folks and others and say this is very complicated stuff. How do you apply it locally? Our goal then is to teach basic concepts to apply this locally by knowing what your local facts are. So I chose a pecan orchard that's around 40 miles southeast of El Paso. And we did this is one of our soil health workshops, one of the 64 we did. We did this in collaboration and partnership with Texas A&M, with a couple of professors there that I've known for years, with some of our folks from humanities. And you're going to say, well, why El Paso? Because of the water situation that I just told you. What happens to us and the rainfall we get, what's stored in the Alpha Dam and the water that goes to El Paso is, you see how the whole thing's connected? What happens in our watershed and the water that we have, someone else will have it or not have it. So that's just the mindset. But at least we've done this on grapes, on a vegetable cropping system, on growing alfalfa, growing silage. All I want to talk about here are the concepts that we're using. So if you look at this photo right here, you can see this trees right here on this row. This is an actual close-up photo of soils that are tilled, because the producer did not want that the natural grass going there to be near the trunk compete. Okay? So what was here was is there a difference in the soil properties and soil types when it's tilled and not tilled? Right, one soil health and the other one is conventional. So right here, this would be conventional tilled soil, which it is, right? Tilled with a herbicide. And this soil here, these are the actual roots of this plant, which were very aggressive on the top, 0 to 6 inches. Therefore now, our emphasis is carbon, 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 carbon. So everything here is driven by carbon. The carbon from photosynthesis coming into the roots and released through the rhizosphere we call root exudates. Another major form of carbon when your soil has a healthy mycorrhizal population is it'll grow an enormous amount of mycorrhizal fungi and it'll release a carbon called a glycoprotein. So this carbon source are constantly pumped into the previous picture where I showed you the macroaggregate. They release that carbon and they stick the particles together and they begin feeding the biology in the soil. So the biology then is eating in an environment where it's well aerated, porous, and there's all kinds of soil food webs. Trophic levels of organisms eating each other, and that keeps the cycling going on because the environment can contain it. So keep in mind that carbon, carbon, carbon is making it possible to have well-aggregated soils, have well-aerated soils. Healthy soils have cooler temperatures in the summer, hold higher water capacity, lower temperature, pH, and provide the environment for nutrients to cycle. So these organisms that are in the soil are relying heavily on root exudates and glomalin to feed the biology of the soil, the majority of which you can't see. And that major carbon source that's taking place all year long, whether it's from your cash crop or your cover crop, is a major carbon source that we want to manage for, and it's above and beyond the crop residues or adding in the compost. You gotta have all of them. The healthy soil, as is already covered really magically this morning here by Brendan, and I know my friend Jay Pierce is going to do an outstanding job tomorrow. We're all going to be talking about the same message, but for a different state and different condition. We're talking about managing carbon in the soil to such an extent that the enormous biodiversity in the soil is constantly fed carbon source. And again, I'm going to emphasize it. The major carbon source coming into the soil is from root exudates and glomalin in a healthy soil. What's making it healthy is the diversity of crops, cover crops, minimum till to keep the soil going in that direction. So just keep that in mind. Okay, you can clearly see here that if we look at a reduced rate still, minimum till, we already see the aggregate where you saw that the soil didn't fall apart right. We said, okay, that came from a soil that has a lot of carbon in the soil, so we minimally disturbed. Look at what happens when we do tillage. On all of our fields that we've been doing this for the last 5 years, all of them that were monoculture, no cover crops, and tilled, all of them, whether they sandy or clay soils, they all fell apart right away. I'm talking about soils that had anywhere from 0.8 to 1% organic matter, whether they were sandy or clay or in between. And these soils that were farmed conventionally, when we give them the slate test or any other measurement, they have poor stability, they fall apart right away. Similar soils on the farmers, the few that have begun making the change, the soil, the first thing to improve in soil health is the soil begins to get off water aggregate stability. It begins to prevent itself, it prevents itself from falling apart because the grains of sand, silt, and clay, like I showed you previously, begin to get stuck together. So that's your first indicator that the transitioning to soil health has begun. Your soil is healthy. You don't necessarily have a dramatic increment in organic matter because you don't. So when your soil starts getting healthy, as we've seen in New Mexico, you might have a soil that was 1% organic matter, next year is 1.1%. The only difference now is that now it's gone into a cover crop rotation, what have you. And the first sign that your soil is getting healthy is that it gets to be slightly structured and it does not fall apart in the water as easy. And then it gets stronger and healthier as it gets to an equilibrium. I'm going to show you here, I'm not going to read this off verbatim, but our first issue in our state is what kind of volume and quantity of water do we have available? Because if you're wanting to do this in our state, this is what we do, because we're in our water situation. How much water do we have from the surface and or aquifer? And what is the combined water quality and quantity availability of that? Because before we're going to begin to attempt soil health in the desert, we have to have a really good understanding of quality and volume of water that we have. Okay, the next step. can you go to the previous? Yeah, give me a second. Okay, for fits, if it's surface irrigation, it's traditional farming, which is a lot of New Mexico, especially northern part. We absolutely, when we're irrigating out of the acequias or our old irrigation system, we absolutely got to move to the laser level field, design properly with borders, so that the advanced and intake oil properties there use water as efficiently as possible. That's the reality. We have many fields that we cannot at this stage go to subsurface drip or sunlight, because that's just long-standing issue. That's how we farm. So the first thing we do, if we're going to do surface irrigation, we've got to get the fields laser level. That's just the rules. When it doesn't apply, we find out what part of the field we're in and what kind of technology matches the water quality, the quantity. And for us, it would be subsurface drip. We've done a lot in New Mexico, and we'll continue to install a lot of it. And we're also doing low-end technology surface drip for typical small gardens, 2, 3, 4, 5 acres. Low-end technology that doesn't require all the sand media filters and high-end technology. And we're also we do a lot of center pivot, sidewalls, concrete ditches, high-flow journals, irrigated pipeline, and aluminum gated pipe. So the next step is we know the volume of water, the quantity, the quality, and how much we have to work with. So if you have so much water, that's what you get to grow your crop. The next thing is, okay, what kind of irrigation system are you going to choose to efficiently get that water that you have available and water quality to grow that crop? Right? Very, very important for us that we choose the system that best fits the area. Okay, the next thing is we start out with a baseline soil fertility and soil health baseline. We've done our field, we've cut our water, the laser level of our field. This is actually an example that we've done here at the Rio Grande Community Farms, which is one of a number of projects that we're doing. We exactly follow this pattern. The next thing we did is we started subsurface drip irrigation. This is run fully certified subsurface for organic. And we're on our third, fourth year. It's working really well. It's taken a couple of years to build soil health, and it's fully served its purpose. The next thing we started off, once the drip was started installed, is we took a comprehensive soil test from a number of our plots at several depths, 0 to 6 inch depths, 6 to 12. We looked at it and we said, what kind of fertility organic matter do we have? Okay? The other thing we did was did the slate test, reactive carbon test, and a few other tests in the field to find out what kind of health is that soil in that we're able to make a decision to plant a cover crop and compost and what have you. So we wanted to find that out to say, okay, this is what we're having. The next thing we did was then, in this kind of case, and I've actually had a Jay here help us develop our first recipes. We planted an 8-way cover crop cocktail mixture. Okay, so I'm giving you one of a number of examples. We planted an 8-way cover crop, and we relied heavily on Jay here and John Smith of North Dakota to help us. And we planted it in several years ago. It was September 15th. By the time we got our first major frost, it was on November 11th. It was on this big. Prior to that, cover crop, those fields had been laser level plowed, and they had horrible soil health. As Jay was there to tell you, horrible things. In that short time, the soil immediately began to get structure and to increase its aggregate stability. That's how it started off. Okay, 3 years later, in this example that I'm showing you, the soils are much, much more water stable and have much more earthworms and much more ready to do their job. Matter of fact, in the last couple of years, we have successfully grown a number of crops very successfully organically on this subsurface strip. So the next thing was is to work on getting the soil healthy. Next, we are doing different versions of minimum till, ridge till, and no till on this site as we are on a few other sites, because we don't know how it works. For one, it took us a couple of years to get a no-till drill and a roller crimper and to learn how to experiment because we didn't know how it was going to play out. So we're on the learning curve trying to figure out how do you do it. That's part of the next step. What we did then is, on the producers that I'm working with, and the example that I gave you, is we made sure, because this is a growing certified organic crops, that we growing diversity of crops in the rotation to make sure that we keep disease, insects, and weed pressures under control. So we want to do a lot of stuff right, early planning, and the goal is we don't want to run into any kind of no more trouble than we need to from not properly planning the ecosystem. Okay? Okay, the final thing, right here where it's pesticides, this doesn't apply to the certified organic, you really can't apply them. But we work with all of our farmers, most of them are conventional farmers, and we're trying to teach them the whole science of how these principles come, because we have to work with our farmers from the ground. But we're integrating this management. We're looking at prevention, avoidance, right? Monitoring, and suppression. And the main emphasis I want to do here is that we're not relying on any one single practice or technology as a silver bullet. They're all tools that we use site-specifically and say, if we do all this stuff right, the end result should be healthy, nutrient-dense crops that very minimal inputs no more than we need to. So this has been, this is the main strategy I want to cover now. I want to cover now the components in a little more detail. As you can see, it's very involved. That's why my approach for the state as we're doing this trainings out is we go with this full knowledge into a community with the cooperation of a farmer, with our partners from NMSU and others, and we give this message and say, here, your Espanola Valley looks like this. When you're in Clovis and Portales, you have water issues, blah, 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 this is the best problem you can do. When you're in the Las Cruces area, you're growing pecans and alfalfa, this is what you can do. This is how your water looks, this is the volume you have, this is your variety, this is probably the best you can do. So I wanted to keep that in mind. Otherwise, there's a tendency of wanting to have a cookie cutter recipe and cover exactly what someone else is doing in another community. Now for growing our pecans on the east side of El Paso, Avenue is one of our reservoirs now that holds water that adds into the Rio Grande that eventually makes it into the Elephant Butte and is eventually water pollution. Okay, for us, we're going to have very little water making it into the Elephant Butte at this stage of the game. That means the water coming out of growing those pecans in El Paso will be primarily pumped water as is happening right now all over the Sierra Valley and the Las Cruces area. Okay, so now, we planned all the previous soil health based on years and years of having water from the Rio Grande and the Rio Chama. Right now we know we don't have it. Now our salinity, total salts has increased in some places up to 2 to 3 times. We have a different game to play with. The amount of sodium, the sodium absorption ratio has gotten much higher. So now we have to work with the previous system that we had not planned. On the bottom, this is an actual field in the Messiah Valley showing water coming out of an aquifer that's so we're gathering all our data and we're figuring out about how much water does it take to grow pecans. And this data is for the Las Cruces area. You can see it says around 48 acre inches of water is needed to meet the consumptive use of pecans. Right? Okay, so our producers there in that area typically will use around 4 to 5 acre feet to grow pecans with good water that's coming out of the Rio Grande. That water is now going to be saltier and not quite as efficient, and we have to use it differently. Okay, so what does this have to do with soil health? On one of the projects that we're doing in the soil health demo in the Las Cruces area, we're using the drip. In the fields that have completely gone to no-till, we're making high-quality compost based on the recipe from the soil food that we incorporated. We're applying that and using no-till and what have you. And we're using subsurface drip and micro-sprinkler. And in some of our fields, we've been able to use 3 acre water. Okay? But we have water now that's saltier. So soil health is going to play a vital role to help mitigate how serious the problem can get with salinity of sodium. And if we go back to our previous picture of a macro aggregate and a micro aggregate, which I want you to keep in your mind, as your planning criteria, right? A soil that is healthy and has good water stability will have the highest water capacity, the lowest temperature, and the best ability to tolerate aeration, drainage, and salinity because the environment is favorable for all organisms. If that soil is still and evaporated with higher salt content, you will disrupt your nutrient cycles, you will raise the pH, you will use fertilizer less effectively, and you will put the plant under a lot more stress. And it gets way more involved. This is talking about the synergy of the whole things are related. So we're back to that. In our state like us, we have no water issues. We have to really get that story straight. What we set ourselves up for a lot of trouble. What I think to do is we take the standard water test. And essentially, in a nutshell, we have soluble salts for our state are dominated by calcium, magnesium, potassium, sodium, a lot of bicarbonate, sulfates, and chloride. So depending on what your electrical conductivity is and how salty that water is, and what kind of sodium absorption ratio, depending on what your aquifer has, that salinity is going to have a certain effect on your soil type and your plant that can tolerate it. Remember I mentioned a while ago that there's no cookie cutter recipe, it's too site specific. If I go into the Los Cruces area and I work with one producer and he's unsure about a given soil type, I cannot use his information to go to his neighbor that's in a different soil type in a different part of the aquifer. The synergy in soil health means is that you have to get a lot of site-specific facts right, especially in irrigated agriculture, because there's too many ways to potentially misread the analysis of the water and its effect on the soil and or on the plant. Okay? Okay, in this example, you can see that we're getting water from a concrete ditch from the canal. Okay. This was prior, before the drought. Now we're filling that up, but with wells. Okay? So now in this example here, we were applying 5,500 pounds of total soluble salts. And I have to know all this came from a lab analysis. It tells you exactly how many pounds all the elements contributed to make the total dissolved solids. Now on the same pecan orchard, on the ones that we're doing, now we're dealing with 12,000 pounds. All we did was exchange water from the Rio Grande to pump it in from an aquifer, and the saltiness level means we applied more than twice the amount of salt. See that? So the salt and the water quality and the chemistry of the water quality necessary, that's a total game changer when you're growing pecans. Pecans are very sensitive to salt and sodium. So unless you're managed, in the example of going to pecan based on soil health, you're going to have a lot of really awful problems. Because you can't just increase the salinity by more than twice, right? Because now the chemistry is dominating them. So now we're talking that the biological, physical, and chemical, they're all related. The biology should always be driving the physical and chemical. The biology, the microorganisms and roots and what have you, they're processing the nutrients to make soil aggregates and keep them structured. So you make decisions to make sure the biology keeps the soil structured. That's the physical part. Because you do that, the physical part will contain the water inside that has the chemical part. So the chemical part is now dominated by the physical part. The physical part is made by the biological. You make decisions to keep the biology at its optimum level of soil health. Because you're wanting the physical to play its role properly, the water stable aggregate, and you want all the chemical properties in there, the soluble, organic, carbon, phosphorus, pH, which all the things that we're analyzing in the soil, whatever. You want the chemistry, the water that's held inside these soils to be at the optimum. Then all of our decisions are going to be made making decisions to keep the soil healthy. So what we are going to have is, this is just a picture of the soluble salts and precipitated salts here. The more salts that we have in the soil, the more stress and the better roots on the plant. Okay? So therefore, we have lower temperatures, very efficient recycling, higher water flowing capacity, reduced evaporation of the water. We will put the plant at an advantage to deal with the saltier environment. If we don't, we will evaporate the water, right? We'll have higher temperatures, affect the nutrient cycling capacity. When we do that, we will force the plants to use more water to cool off. Remember, the plant's now dealing with an additional stress in not taking water. Remember the first macro aggregate where I told you we wanted it to be stable? Okay. When the water is taken, the plants are taking out the water, it's held in between particles, and we call that matrix potential retention. We simply insert a tensiometer, and I will use very simple tools for the farmers to do it just I'll insert a tensiometer at 8-inch or at 12-inch. Look at your healthy soil, look at your poor soil. What do you see different about the tensiometer and the healthy soil? It will be under the least tension for a given irrigation interval. So what is that telling us, right? Put in a tool to make a point. It means that the soil, the plant in the healthy soil was most effectively able to use water in a soil that had soil health. If it didn't, you had problems. So a simple tensiometer tool is one of a number of tools that I've used effectively to make this concept clear. Because now, remember I told you that we have salinity that is about twice the saltier or so. We have twice the amount of soluble salts dissolved flowing inside the water, and there's a little pool between the particles that's water held in microbursts, right? The plant now has that additional stress in addition to pulling the water off that's tied to the side of the capillary action, adhesion and cohesion. So now we know that the plant's under stress. That's a fact. If we don't do everything to help the plant do all the stresses, these are stresses that will multiply the plant will begin to have die off or something somewhere. In this case, of the country. So we know the plants won't show up. The countries are very unforgiving. Yet any time that you don't go with that intention in mind, the trees burn. The bottom part of the leaves die and the leaves fall. But this can happen in any crop. Once you exceed a crop salt tolerance, it'll happen to any crop. Whether it's corn, onions, or chili, it's the same story. Okay, let's look at a crop salt tolerance. If I'm irrigating with an EC of 5.3, that's extremely something. We have a few places like that in Mexico. If I was growing a barley crop, I would have 0 yield tolerance, right? Because it's a salt tolerant crop. And look at right here, a lot of pecan. If I irrigate with a 2.4 EC, I will have a soil saturation of 3.2, and I will have a yield loss of 25%. The regular our ECs have gone from 1 to 2.5 to 2.5. So what happens if the pecan industry, we are irrigating, and we are in some of our wells with an EC of 2.4. It has the potential to drop the yield by 25% because it can. But it can drop it way less if you measure that in the context of soil health, right? Remember that everything is context. If your soil has gravity stability versus one that falls apart, and you take a water test and a soil test, what have you, you compare the results based on the environment that it was exposed to. Otherwise, you won't have context. Otherwise, you can do the soil test and say, I'm not sure exactly what to do. Go ahead. This is an actual. Can't see it that way. This is an actual photo that's exposing the entire root system of the fully mature pecan, the regulated tree 20-some years ago. You can see that pecan, though it has roots that can go quite deep, 6, 7 feet deep. The majority of the water uptake in the pecan, in spite of the trees that were 30, 40 years old, we found the majority of the water taken up at the 0 to 12 inch depth, and then another batch of water at the 12 to 24. Whenever we put tensiometers at the 3-foot depth or just did a feel and hand appearance, very little moisture taken out at 3-foot depth. So again, understanding your root system, your soil type, and the context in which you are making management decisions. This is the actual photo. The water table there is at 5 feet. This is on the El Paso. It's no longer at 5 feet, it's way deeper because of the traffic. We had around 0 to 14 inch depth of the silty clay loam. Okay, so we have the silty clay loam underlaid by a sugar sand. What we find then is that we have the majority of our soil fertility in the top foot based on soil testing, based on actual properties that we've seen. Once we go into the sugar sand, we have very little fertility potential because it's coarse sugar sand. And we know that very little activity is taking place because when we use a pocket auger or a tensiometer or whatever, we know it's wet. So if the soil is wet 1 week now, 2 weeks pass, and your water is still wet, and you need water. So that means we're managing that top water again. We're back to that. So the other thing is knowing your soil type.